What's the difference between preload and spring rate? Does adding preload stiffen my shocks? Can I balance the weight distribution of my rig with preload or springs? All great questions. On this channel, we explain the science behind your grown-up toys. First, let's understand the physics of how springs work. And since this is mainly an RC crawler channel, we will see how it applies to rock crawlers. First, the theory. Let's check it out. A coil spring is simply a torsion bar that's been wound up into a coil. It acts exactly the same. The wire twists when the spring compresses. If you have more coils in the spring, you will have a longer wire and hence a softer spring. The longer the wire, the easier it is to twist. The thicker or larger diameter of the wire, the harder it is to twist. Here is the equation for the twist in a torsion bar. Now, before you jump off, let me show you the relevance. Here are the variables in play. This is the angular twist. G is the modulus of elasticity, which is a material property. D is the wire diameter, L is the length of the wire, and T is the torque applied. Now let's look at the equation for a coil spring. K is the spring rate or spring constant. That is not yet the deflection of the spring per a given force. Notice that there is no F or X in the equation yet. K is the spring rate. G, again, is the modulus of elasticity, which is a material property of steel. D is the wire diameter. N is the number of coils, and D is the average coil diameter. That diameter is measured to the middle of the wire. And N and D are simply numbers that are used to calculate the total length of the wire. Once we have calculated the spring rate, we apply a second equation to figure out the deflection based on the force applied. This is also known as Hooke's law. Now let's compare the two equations. The result of these equations is a quantity of physical displacement. One is a linear displacement, the other is an angular rotation. Both have a force input. One is a torque, and one is a linear force. These variables simply describe the length of the wire. On the coil spring, the number of coils and the diameter of the coils are simply a mathematical way to determine the length of the wire. This is the modulus of elasticity, which is a material property. For example, steel is much stiffer than plastic, so steel would have a higher modulus number than plastic. Both have the wire diameter. Notice that it's to the power of 4, which means the effect of wire diameter in the equation is very big. Since it's on the bottom of the equation, that means it has an inverse or negative effect. The larger the diameter of the wire, the less deflection, to the power of 4. That means if you double the diameter, the stiffness goes up by 16 times, not just 2 times. You can see that both equations have the same variables. The 8 and the 32 are simply algebraic resultants that rectify the geometry of a round wire. You will notice that the overall length of the spring is not a variable. That's because it doesn't matter. If you take your spring, stretch it really long, permanently deforming it, you have not changed the length of wire. You still have the same number of coils. So stretching your spring doesn't make it stiffer or softer. Only adding or subtracting coils makes it softer or stiffer, respectively. Okay, enough theory. What does this mean for your rig? Let's look at spring rate. Here is what spring rate looks like graphically. As the shock and spring compress, the force goes up. In this case, we're looking at a 10 gram per millimeter spring. That means it takes 10 grams to compress it 1 millimeter. Also remember that we are looking at only the reaction coming from the spring. If you watched my video on tuning with shock angle, these charts would represent something a little different in those videos. The slope of the line is the spring rate, or the spring constant, or K, from the prior equations. Slope is calculated by rise over run. You might remember this from junior high algebra. So let's look at this hypothetical spring. And note that this is with 0 preload. The rise is 200, and the run is 20 millimeters. Do the math, that equals 10 grams per millimeter. The name of the spring is often simplified to just a 10-gram spring or a 50-pound spring. What that really means is grams per millimeter or newtons per millimeter or pounds per inch. It often just gets abbreviated to the force only. For example, look at this Fox spring. It says 300. That is technically a 300 pound per inch spring, and it's abbreviated to 300. This 3.5 is the maximum compression the spring will handle. If you follow the math, you will know that it takes 1,050 pounds to compress this spring 3.5 inches. That's 300 times 3.5. If you have a higher spring rate, the slope of the line changes. In this case, the spring rate, rise over run, rise of 300, same run of 20, is now 15 grams per millimeter, and the slope is steeper. Now let's understand preload. Preload means adding force to the shock by compressing the spring. But the shock does not change length, only the spring does. Assume a spring that is rated at 10 grams per millimeter, and the shock has 20 millimeters of stroke. To compress the shock 1 millimeter, it takes 10 grams. To move it 5 millimeters, it takes 50 grams. No matter where you are in the travel, or no matter where your preload collar is, it will always take 10 grams to move the next 1 millimeter, or 50 grams for every 5 millimeters. Preload does not make your spring stiffer. You should also know by now that preload doesn't make the length of wire in your spring any longer, so it can't possibly make it any stiffer. Here's what preload looks like on the chart. The initial force to move the shock has increased, but the shock has not moved. You don't live topped out. Shocks function out here in the travel. Notice that the slope is exactly the same. It's just shifted. Buggies, trucks, touring cars spend most of their time in the beginning third of the travel. So they have positive travel available to absorb bumps and a little bit of negative travel for when the train drops away, like a ditch or a pothole. Trophy trucks sit much deeper, around 50%. RC crawlers generally run very high droop, sometimes called sag in other industries. I'm using the term droop and sag and ride height interchangeably. I hope that's not confusing. You want to consider what the spring is doing near the end of the stroke because that's the zone where you spend most of the time. Remember, each increment takes the same amount of force to move the shock. Even if you're starting at 90% droop, the last 10% of compression, which is 2 millimeters in this case, will still only take 20 grams to bottom out. 10 grams for 1 millimeter, 20 grams for 2 millimeters. This is what happens when you add preload. Let's say you add 50 grams of preload. Your response moves from the gray line to the orange line. Let's say you had your vehicle set up at 50% droop. Your position in the travel and the shock length and the ride height will rise, causing your droop to go from 50% to 25%. This is the only thing that preload does. It changes your ride height. The force required to move the wheel has not changed. The slope of the lines are still the same. Remember rise over run and spring rate? That has not changed. So your shock and your suspension response has not gotten any stiffer. 25 to 50% takes 50 grams. 50 to 75% also takes 50 grams. Now, one thing that does happen is that now you have more travel. If you moved from 50% droop down to 25% droop, you have a whole lot more travel. And with that extra travel, you can achieve a higher bottom out force. But that's not coming from a stiffer spring. It's coming from more travel and at the expense of less droop or a higher chassis. So your bottom out force goes up, but so does your ride height, and that's not the same thing as a stiffer spring. So when do you use preload versus spring rate? Preload adjusts your ride height, that's it. Spring rate adjusts your suspension stiffness. Again, we're only talking about the spring itself. Remember, you also have the shock angle and progression to assist with your tuning, which I talk about in these videos. Here is an advanced tuning method that combines preload and spring rate to achieve a different response. Let's say you're happy with your ride height, and let's say it's at 30%. That should be one of the very first things you define on a new vehicle, your ride height. You aren't going to be changing that very much or very often. Let's say after some driving, you aren't using all of your travel. You hit a jump, but your shock never reaches full compression. This should lead you to conclude that you want to use a softer spring so it compresses more easily, so you take advantage of all your travel. The opposite is also true. If you are blowing through your travel and bottoming out too hard and too frequently, you would want a stiffer spring. Here's what that looks like. You're going to switch to a softer spring, a lower spring rate, let's say 10 grams per millimeter in this case. Before you had a 15 gram per millimeter. The first thing you need to do is add preload to the softer spring so that your ride height is at that same 30%. You do this by measuring the ride height on your actual car and matching it between the two spring settings. When you've done that, look what happens to the bottom out force. Originally, it took 300 grams to compress the suspension all the way. Now it only takes, let's say, 240 grams to reach bottom out. And notice that you still have the same ride height and the same amount of shock stroke to absorb the bumps, 30 to 100%. Remember this chart? If you only change preload, yes, you are changing the bottom out force, but you're doing it with additional ride height and shock travel. This is not the right way to change your bottom out force. You want to do it this way with spring rate. Then use preload to reset your ride height. I've heard some people say you can balance your corner weight with preload. The problem is it makes your vehicle sit crooked, and you want it to be level, especially left to right. Anytime you turn the preload collars, your shock length changes, and that makes your vehicle sit crooked. Don't try to weight balance with preload, unless you only turn left. NASCAR can use cross weight and wedge effectively because they only turn left. On any other vehicle, you want to use weight to balance your weight, and that's pretty easy to do on an RC crawler. Start by getting the car level side to side. Adjust the preload on the front shocks first, then do the rear, then double check the front. Then set your attitude, front end higher or lower, depending on what your clearance preference is. Adjust both the front or both the rear at the same time so your left-right balance is maintained. If you are running full droop, this is far less important. If you're using a scale and balancing system, weight balance your car with weight, not preload. Shift your components around, take out weight, or add tungsten brass or lead weights wherever needed. Trying to use preload to balance your car will just make it sit crooked. So, what does all this mean for an RC rock crawler? There are two schools of thought. Let's call it suspended and full droop, or essentially unsuspended. If you are running full droop, then the theories are different. I want to clarify that the phrase full droop can have a completely opposite meaning. In some worlds, full droop means fully extended. This video follows the common RC crawler definition of fully compressed. I can't think of any other vehicle besides an RC crawler that would run full droop, which is what makes crawlers such a fascinating and unique suspension challenge. I've never seen someone try to explain how to tune for full droop, so we'll tackle that in an upcoming video. But here's a teaser. If you are running full droop, you are doing it one of three ways. Super light springs, too light to spring your sprung weight, or no springs, your shocks just sit bottomed out, or something that other industries would call negative springs. This means hair bands, pen springs, or other shock bands. These are negative springs that act against the positive coil springs. They effectively cancel out the positive springs partially or fully. I will do a future video on this topic because there's a lot of confusion here as well. Here is a vehicle that is suspended. You might be running 80 or 90% droop. This means your chassis is sitting on the springs, not bottomed out, and you have 10 to 20% positive suspension available for bumps and terrain. Your negative travel is used for articulation. Everything I've explained will apply here. Use preload to adjust your ride height and keep the car level. Change springs to change your shock stiffness. Use weight to balance the weight. The variables in play are these. You have the force of the weight of your chassis pushing down. This is your sprung weight. You have the force of your axle, which is usually very heavy, also pushing down. This is known as unsprung weight. You have the positive spring or the coil spring pushing your axle away from the chassis. This is good for pushing the axle into the terrain to maintain contact. And you may have a negative spring, hair bands, pen springs, pulling the axle toward the chassis. This is good for holding the suspension down on steep climbs and descents. The problem is all these forces are invisible because the shocks are sitting completely bottomed out. You can't really measure them, and you can't visualize them like you can with a sprung setup. When your chassis is unloading, what's really happening is your shock springs are pushing the chassis away from the axle. Because the terrain is so steep, there's not enough chassis weight to keep the shocks compressed. That is combined with the torque coming from the rear wheel drive. So you can add back downforce with negative springs, if that makes sense. Also, you cannot hold the front end down through rear linkage. That is a myth that perpetuates within the RC crawler world that has no basis in physics or suspension design. I've produced a number of videos on that very topic. Some people love negative springs. Other people argue that if you tune your shocks correctly, you don't need negative springs. They are just a band-aid. My rig gets full articulation and generally stays compressed on climbs and descents. So what more could you want? Here's how I do it. I run no positive coil springs and very light hairband negative springs, front and rear. You can actually buy hairbands in different stiffnesses and they're cheap and an easy way to experiment. You can also buy shock cord and make your own loops with different stiffnesses and lengths, which is next level tuning. If you're in the full droop camp, here is how I would propose you start. If you put a positive spring and a negative spring together, you just get a new softer spring. So look at these two things. You want your final resultant spring rate stiff enough to push the axle down to articulate and match the terrain. The axle should drop from its own weight when the terrain falls away, and usually doesn't need the help from a positive spring. Try taking off your coil springs altogether and see if your wheels still follow the terrain. I bet they will. You will want lighter oil if you try this. Secondly, you want your rate soft enough to prevent your front end from unloading or your chassis from lifting up under high torque on steep climbs. And don't forget descending. You want your rear to stay compressed and low on steep descents as well. You want just enough to hold the suspension down and no more. It doesn't take much. There's definitely a sweet spot there somewhere, balancing the positive and the negative springs. So, what did we learn? Spring rate and preload are different. Preload adjusts your ride height. Spring rate adjusts your stiffness. Preload doesn't make your suspension stiffer. to droop or not to droop, that will completely affect your tuning approach. Negative springs cancel out or reduce positive coil springs. Now, go get sprung. Or don't.